Hello, today I'm having an interview about the topic of sparse experts. Now, ironically, the people are absolute experts in this type of models. These models, they are huge. They're usually language models, but they don't have to be. They're usually transformers, but they don't have to be. What they do have in common is this notion of sparse experts. These models go up to the trillions of parameters, and they achieve this via sparsity. Now, I want to do a very brief introduction of what sparse expert models are, and then we'll dive into the interview right away because I don't want to keep it from you. So let's look at a transformer model. Usually I have some sort of an input that is tokens, a sequence of tokens which are represented here by circles. And what I'm going to do with these tokens is I'm going to alternatingly push them through different layers. Now, one big layer type that is common in transformers is the attention layer. We're not going to talk about the attention layer today. All you have to know is that it takes in a sequence of tokens and it outputs a sequence of tokens again. Ideally, the same amount as went in, which I failed to draw here. The other very common big type of layer in these transformers is what's called the feed-forward layer. Now, the feed-forward layer is just a linear layer, and every token goes through this linear layer by itself. So every token individually goes through the same transformation. And thus, as we do this with all tokens, again, we end up with a sequence of as many tokens as we input. Now, a sparse expert model isn't very different than this. The attention layers commonly aren't really touched, so that works just the same. However, in the feed-forward layer, we see a big difference. Notably, we don't only have one feed-forward layer, we have many. So here is feed-forward 1, here is feed-forward 2, here is feed-forward 3, and here is feed-forward 4. Each one representing a different individual linear transformation of a token. Now, when we talk about sparse experts, these things here are called the experts. They're called the experts because they're thought to specialize in very specific tasks. And the goal in sparse expert models is to route the tokens to the corresponding correct experts. So every token goes through what's known as a routing function. We're going to talk about this routing function in the interview, but in essence, it is a very simple, usually something like a linear function or a simple transformation that decides to which of the experts any given token is routed. So sometimes even in sparse expert models, a token is routed to multiple experts, but in the newest iterations, the tokens are simply routed to one single expert and none of the other. Usually this is done, as I said, by some sort of a linear transformation followed by a softmax to decide where the token goes. So every token would be assigned to one expert, and that gives the possibility of scaling these models up dramatically. Not only do you save a lot of compute because the tokens only go to one place, ergo you only need to compute that one thing for that particular token, but also there's the opportunity to massively shard and parallelize these different experts across different machines. As you only need to route the token to one place, that means you dramatically reduce these big all-to-all reductions. They still happen, but not as much. So as I already said, the biggest models have trillions of parameters. You need to take a little bit of care of how you then aggregate the tokens once they come out of the experts. So essentially what you want to do is you want to carry over the likelihood from the routing function up here, but this is a minor detail. Minor details are important, but you know. So I know it doesn't look like much, but these sparse expert models really have the potential to massively scale up our current efforts in AI. And I have no doubt that they're going to play a role in the near future when we're looking at bigger and bigger models. Because at some point, the purely dense models will reach sort of the limit of what's physically doable. And then it's a good opportunity that we have models that can go even larger. All right, so without further ado, let's jump into the interview. I hope you're enjoying yourself. If you do have any sort of comments, please leave a comment, share the video around if you like it, and I'll see you around. Bye-bye. Hello everyone, my guests today are William Fedus and Barret Zoph, who are engineers and researchers at Google, Google Brain, and have been diving into large models, specifically sparse expert models, which are models that feature this notion of experts and also have a notion of sparsity. And hopefully today we'll discover what this is all about. Specifically, we'll talk broadly about 3 papers in a long line of work. One is the Switch Transformers paper, which was really, I believe, one of the first papers that just had like massive amounts of parameter. Was that like probably trillion parameters? It was big.
1.6 trillion parameters. That's right.
Yeah, it's insane. And then there's GLAM, which demonstrated really nice scaling laws with these sparse experts. And more recently, there is designing effective sparse expert models, which, as far as I can see, is also a bit of a maybe a summary, recommendations, more of a what we learned type of thing. So William and Barret, welcome to the channel. Thanks so much for being here.
Yeah, thanks for having
us.
So can you give us just a little bit of context what you mean when you say sparse expert models?
Barret, do you want to proceed?
Yeah, sure. So this is a great question, especially since the word sparsity crops up in like many different aspects of deep learning, whether it's, like sparse attention or, various other sparse paradigms. So yeah, sparsity in our case means that each input can get different subsets of parameters. So that's kind of like the main sparsity that we're talking about here. And it's like, it's a very natural concept, right? Like normally in like a dense transformer, for example, you have, a word embedding, and, any word will have the same parameters and compute applied to it. And in sparse models, typically what happens is you have the same amount of compute, but you can have different subsets of the model parameters be like, acting on the model inputs.
And what does that mean in practice? So we're talking mainly about, let's say, transformer models here. No, is that a good characterization of things, or do you see sparse expert models in a more general sense?
Yeah, I mean, these things actually almost sort of like cropped up originally as almost like in the context of like ensemble type methods, where you have a bunch of like almost like fully independent models, and then you're sort of using these as like, each model is an expert. But the common paradigm as of like 2022 is sort of experts as a layer. So this was like really popularized by Noam Shazir's work in 2017, outrageously large models. And in that context, they were actually inserting it in between LSTM layers, which was like the prevailing like recurrent architecture at the time. Most of the things, just because like the world has sort of shifted towards transformers in, it seems like almost all modalities now, we're often thinking about experts as a layer inside transformers. Typically, we're sort of doing this at the feed forward. So these blocks that just sort of independently apply on the different like tokens. But we've also kind of considered it in self-attention layers. It's just sort of like a very general concept. But yeah, typically in transformers.
So you have this notion of an expert, which you say is sort of a specialized function or something like this. And then there's often this thing called a router. How does information find its way through these experts? What are the general principles in that? And why would I even consider doing something like this?
Yeah, so great question. So yeah, so you have this figure up here. And so one thing to note is that basically if you only had a single expert, it essentially reduces to just a normal dense transformer. So the interpretation is pretty natural. And in almost all of the ways people are doing sparse expert model nowadays, there's some notion of a learned mechanism that for, embedding at the current layer, you figure out what expert you should, send this representation to. And this can be ranging from, very simple to just like, a simple softmax function over the total number of experts to, very complicated, linear programming type solutions that have a more like globally optimal solution. So yeah, so this is kind of like the paradigm, and I think it's a pretty natural one. So even if you wanted to only, apply one set of weights per representation, now you have the option of just, instead of always applying the same weight matrix, now you can, maybe have a selection of, in this figure, 4 different weight matrices. And the way that, we've done this in our work, and I think is the most common, is it's just as a single feed forward network. So you take your input representation, and then you just, apply it with something that's going to be like, the model dimension by the number of experts. And then you apply like a softmax function to get like a probability over all of the different experts. And in our switch transformer work, the routing was extremely simple, where it's just like you just send it to the highest, like the highest expert with the highest probability. and then you just simply route it to that expert, then the output of that computation gets scaled by the router probability. So if it was like, oh, with 0.9, send it to expert 2, then when you have the output of that computation, you scale it all by 0.9.
Do I remember correctly that there was some paper that, was this an older paper, and this might be getting very technical for a second, but was there an older paper that said something like you always needed to send it to at least 2 of these experts, otherwise it's kind of unstable? Is that an older paper or a newer than yours?
It actually wasn't instability that they were cautioning against. It was more this idea that we're doing this like weird discretized operation. So instead of using like reinforcement learning to sort of like update on the experts, we're kind of doing this like kind of hacky backpropagation through these like softmax operations, which had been masked. And the idea that top 2 or greater was necessary because they were thinking, well, I'm creating a probability distribution for this token, for this word, over the available experts. If I don't have at least 2, I can't tell whether expert I or J was sort of better for this one. So it's like, in order to have, the hypothesis was sort of like a useful gradient signal for the router, it has to know, well, should I have sent it to I or J? And then we just sort of didn't follow convention and did 1, and it also seems to work just fine. I think in part because you're sort of doing this sort of normalization. So you can still get an up weighting or a down weighting if you select an expert. So it's like, oh, if that expert selection worked out well for you or worked out poorly for you, you can then sort of adjust the embedding for that expert. And then you, at the next pass, if you saw that same token, you're still doing this like softmax distribution. So you're kind of like up weighting or down weighting it. So I think that's sort of like the gist of the mechanism. And this I think this idea was at least from 2017. It may have predated it.
Mm-hmm. Could you maybe, now that we're talking about history, trace the evolution of this line of research a little bit? You already mentioned this existed as sort of ensemble methods inside of it. I'm talking now specifically about sparse experts within transformers, which are the things that allow us to really scale up to these giant models. What's sort of the line of research? What are the original things? I'm going to guess this work is among them. And what were the improvements that happened since then in this field?
Barret, do you want me to go or you?
Go for it, Liam.
Yeah. So I mean, like going back 30 years, like you have like Jordan's and Jacob. This obviously predates Transformer because Transformer was a 2017 development. So I mean, the concept is very, very old. I think it just kind of like resurged in popularity. I'd say like the very first sort of use of mixture of experts in Transformer was Lepkin et al. In 2020. So this is G-Shard. And it just showed really remarkable improvements in translation. What they were doing was, analogous to Switch Transformers and these other works, is they just sort of substitute these feed-forward blocks with experts. And in that case, sort of also similar with Switch Transformer, they had many, many experts. I think in that case, it was thousands. And they were showing really significant improvements over state-of-the-art translation models. I think as the field has sort of evolved, as we've sort of like learned a bit more about it, there seemed to be this like kind of general trend of like, okay, cool, we can pre-train these models, or like in the case of translation, there's no big distribution shift. When you're training to translate, you're also doing inference to translate. But in Switch Transformer, we found, okay, we'll pre-train to, improve the perplexity, improve the prediction of next token. And we were getting significant improvements. But then when we took it under a data distribution shift to fine tuning, it was performing quite badly with many experts. So I think there's been this trend to try to balance the computation and the parameters a bit more. So I think some of the prevailing models have actually, in Transformers, have actually gone towards fewer experts. So 16, 32, 64 experts, not thousands of experts. So that's kind of like the lineage of mixture of experts, and then like mixture of experts in the context of Transformers.
And so in that context, if one expert is the classic transformer model, and that seems to not work as well as many experts, but too many don't work, what is the abstraction that I can think of for an expert. Like, what does an expert learn? What is an expert responsible for approximately? Do you have any idea what happens? Like, how does it make sense that the optimal number is, let's say, a few dozen and not super many, but also not one?
Yeah, so great question. There's like a few parts to this. So one, like, I think it's really just like an empirical observation right now that, 16 versus 64 versus, 2048 versus 10,000. Like, it seems like the expert numbers in the middle, like it's not from the standpoint of like on a per step basis. More experts typically don't make things worse. Usually it's like better or about the same, but things start to level off. But it's very inconvenient to have a lot of experts because it's just this like a huge memory footprint. The way that the models are distributed, it's not really amenable towards typically, unless you have like tons of, parallel cores going. So like actually the observation where you kind of want to actually have like a middle amount of experts is a lot of the times actually driven by just the like practicality of then like training, serving these models. Yeah, in terms of like what these models are actually learning like intuitively. So we actually studied this in our most recent work, kind of looking at, each expert, what are they specializing in? What are they learning? And interestingly, they kind of specialize in some shallow concepts, which you would think maybe there would be like only really deep things going on and it would be kind of hard to inspect them. But, we noticed like, oh, there's like a punctuation expert or an expert that will, talk about, like proper nouns, which we thought was pretty funny and maybe not super intuitive for, how.
Yeah, Yannick, actually, if you want, you could switch over to the recent paper and we actually have a figure which sort of shows some of these things. So you can kind of like follow along and see how shallow these things actually are.
One. Yeah. So this would be different. So you found an expert, or in this case, multiple experts that focused on these sort of things. So there's conjunctions, punctuation, verb, visual description, which is interesting because that's kind of I want to say like a higher level thing than just a punctuation, right? Counting numbers. Yeah, how do you make sense of this stuff? Like, what's going on?
I think we were sort of expecting maybe like a higher level of description, but sort of like representation. I think we've just started to sort of like crack and like look into these models to actually see what's going on. That obviously like one big specialization that you're seeing here are these sentinel tokens. To make sense of that, we were sort of doing pre-training where it's sort of fill in the blank tasks, and a blank is sort of represented by these like little sentinels. So like extra ID 10 represents like, the blank 10. And we often really frequently see experts sort of specializing on these blanks. So that's sort of an interesting thing. And then I think that also might segue into maybe you want to actually, given this sort of like, observed specialization, maybe you actually want to make some experts higher capacity or give them more compute to sort of do things that might be harder. But honestly, I mean, this is still very early. It'd be interesting for sort of like, some of the interpretability lens that like Anthropic has on some of the recent transformers to be applied to like some sparse expert models. Some questions we've kind of received are, what is the interplay of expert specialization with sort of like self-attention specialization? And that's honestly completely open. I think we were just sort of putting this table forth to the community to be like, well, we started. It's not exactly what we would have expected, but definitely kind of like a call to dig further and hopefully like, further improve things.
With the also, I believe that this was here already in Switch Transformers, this ability to distribute these things across devices that comes naturally with having sparse experts. So sparsity meaning in this case, I only send stuff to one or a few experts. And there came the ability to shard this across devices. How practical is this really to like when would I do something like this? At what point would it become practical and useful and the best thing to do to communicate across devices for my experts?
Yeah, so really great question. And I actually think this is the reason why the method works so well, actually. So the standard way I would say people are doing distributed training of these models is they have, either fully data parallelism, which means like, each machine has the same set of weights, but different slices of data, or a blend of data and model parallelism, where it's like, kind of a mix where certain cores have sometimes different weights or sometimes different data, and then you communicate stuff to make it, emulate like a full model. Mm-hmm. But I think experts, one really easy interpretation of this is like, let's say you have a model and you're using data parallelism and you have 4 different machines. A really natural way to overlay experts on this would be you just have 1 expert per machine. And then, so this is like a really nice interpretation, because then when you have all of your, local data per core, you have the router weights replicated, but then you just figure out what expert they need to go to. And then that's when you kind of, shuffle all the tokens around to the machines, do all the computation, and then shuffle them back. And this makes it really nice because then per machine, you actually never have any more parameters than you would have had just with a dense transformer. But now you have experts. So it's actually like a really nice way of kind of, thinking about how to design the models would be like, you have this many cores for data parallelism, just have that many experts. And that's actually a paradigm that Liam and I use a lot when designing these models as well.
And yeah, I mean, I think as soon as you have this sort of like distributed model where you're already going across accelerators and devices, you do already have these communication patterns, right? Like you need to get activations to a certain place, you need to like get gradients to a certain place. So you already have these sort of like all reduced communication collectives. Expert model is going to introduce all-to-all communication patterns. So that can be like a more expensive thing, especially based on like your topology and the bandwidth between all of your networks or between all of your devices. But yeah, so I mean, this is something you sort of have to like kind of empirically test, like, okay, how much does this architecture kind of buy you in terms of performance on your task versus the additional costs of all-to-all communication. But you will be communicating across devices for these big models regardless to train them.
Yeah. So this is a good, I guess, a good segue, because you can achieve these giant models, like trillions of parameters, using these sparse expert models, because naturally I can parallelize these experts. It doesn't cost me really much more compute because any data point or any token only goes to one single expert. There is always a bit of the, let's say, the question of how comparable this is to the dense models. It was often, I don't know if this is a latent feeling that I get from the community, but people would rather have the 175 billion GPT-3 model compared to the Switch Transformer, even if it is trillions of parameters. Is there some sort of division factor where I could compare to a dense model? Or do you think that it's an entirely different nature of a function that's computed here?
Yeah, so this is a really great question. And I think there's a lot of different ways you have to kind of look at this to figure out if a sparse model is right for you. So I think actually in a lot of applications, if it's like, hey, I want to train the model with the smallest memory footprint, so I can just be using it on the smallest amount of devices as possible, a dense model will always be better. Like I think on a per parameter basis, dense models are going to be performing better. So for those types of applications, I'm like, yeah, I don't think it makes sense to be using sparse models. Maybe you want to just train the best thing that you can fit onto your local 2 GPU machine or like a 10 GPU machine and do really kind of, low throughput, feeding in data to this, like not high or anything like that. I think sparse models are good where you're going to be training a model and you're going to be hosting it on a lot of machines and you're going to be having like a lot of like high throughput going through it. So a lot of queries, a lot of stuff going through it, because then things can be batched together and then the models actually become pretty efficient. So I think that's kind of one lens to look at when you would want to use a sparse versus dense model. And I think the kind of second lens is that, for a given amount of like, GPU or TPU hours on like a compute cluster, what model will get you the best performance? And I think that's the lens that we actually would spend a lot of time looking at for like, pre-training models in this paper. Like, oh, you have 512 TPU chips and I give you, X budget training hours, is a dense model or sparse model going to give you the best pre-training performance? And I think our assessment was that, yeah, I think the Pareto optimal model typically is a sparse model in that setup.
Yeah, and like comparing parameters, especially between a dense and a sparse model, is just, totally incomparable. So using like GPT-3 and then like our largest like Switch Transformer model, it's just wildly different amount of compute in our case. You can't infer that from the parameter budget. So I don't know what the compute ratio was between the two, but far different. Our 1.6 trillion parameter model was actually only doing about as much compute as a billion parameter model. So for each token, it was doing roughly a billion parameters worth of flops, and whereas GPT-3 is doing 175 billion parameters worth of flops. So you can sort of like tune this, and DeepMind has sort of also tried to come up with like a characterization of scaling properties, far more like robust than we've been able to do, of sparse expert models, and try to come up with like a dense model equivalent. So like that might be like an interesting work to sort of like refer to in the future. But really it's just like, practically speaking, it's like, okay, I give you these accelerators for this amount of time. What's like the best model? So that's like probably the fairest comparison.
Have you seen this pathways paper?
Yes, definitely.
That came out. Like, how does it play into something like this? Is it gonna make this easier? Is it gonna make it superfluous? Like, how does the sort of ability to schedule things heterogeneously across devices, or does it enable new possibilities in the sparse expert world?
Yeah, so great question. So one thing to note is like, okay, so typically you have dense models, and a dense model, like every input will have the same amount of compute and parameters applied to it. And sparse models, now you have the same amount of compute, but different parameters. And I think the kind of natural next step that I think makes a lot of sense to both Liam and I is that now for each input, you have a different amount of compute applied as well. And I think pathways is really exciting, again, like you kind of mentioned, for like the heterogeneous compute, where we want to have inputs that might require, different parameters and also different amounts of compute. Yeah, and I think, a framework like this is going to really open up like a lot of really exciting research avenues along that direction. And I think it feels like a very natural interpretation for kind of where our models are headed for in the future.
Yeah, like right now, it's like our experts are all sort of completely homogenous. They're all the same size. They do the same operations. Pathways, you could be like, oh, this is like a recurrent expert. This is a huge expert. There's a group of small experts. You could just be a lot more flexible in design. And like, sort of like alluding to that a little bit with when we were sort of looking at the visualization, it's like, oh, wow, a really consistent thing are experts that want to specialize in these like fill in the blank tokens, these sentinel tokens. Perhaps that might be an avenue or an area where it's like, oh, let's dramatically increase the compute here. This is, oh, hi, Kat. This is like an area where we like a lot of extra compute could really be helpful. And there wasn't really an effective way to do this with the existing infrastructures before pathways.
Is there a yeah, sorry, that's lost the train of thought. Explain to me a little bit how GLAM improved upon Switch Transformers. Like, what's new? What's exciting there?
Yeah, so I think GLAM. So one also thing to note is like there's kind of a right now division of two different types of model classes in like the language modeling space, I would say. So one is like these decoder only models where it's just a single set of parameters, and it's like you're just predicting the next token like autoregressively. And this is like what GPT-3 is, and this is also the kind of architecture that GLAM studies these models in. So the other class is these like encoder-decoder models like T5. This was also G-Shard. This is kind of what also we studied in Switch Transformer in our most recent work as well. So I think GLAM did a few things. So one, they really, I think, pushed the scale of these models. So like while our original model in Switch Transformer had more parameters, like GLAM had like much more compute applied per token. And they studied these very extensively with decoder-only language models. And yeah, I think their main comparison point was to GPT-3 as well. So they were studying a lot in the context of few shot and like one shot evaluations. whereas I think a lot of our work actually centered around like fine tuning the models.
Mm.
But yeah, I think GLAM really like pushed the scale of these, especially in these decoder only language models, and showed that like, yeah, you can get as good of quality as GPT-3 with like, huge computational training savings as well. And did a lot of really good work in that space.
Is there a functional difference between the sparse expert routing or anything around this in GLAM, or is it mainly what you said with decoder only and applying more compute, scaling it up?
So actually, there is a few differences that are more nuanced and technical. But yeah, at a high level, there's a routing function, and they actually route each token to two experts. And actually, there's like some of the differences in these models comes from like how much buffer you give each token, each expert, because you need to have like fixed batch sizes for all of the experts ahead of time. And so what can happen is like you can't guarantee that like there's going to be perfect balancing among all of the tokens getting sent to experts, so like experts can overflow. And there's this key parameter that we call the capacity factor. That's probably the single-handedly most important parameter when designing a mixture of expert models, because it just has such a huge impact on the communication costs, compute, and everything like that for how much buffer you should have. And yeah, I think a big difference from GLAM versus our models is they actually use like a much larger capacity factor than we've used in our other works. But yeah, the routing algorithm is essentially the same.
Mm. That is, yeah. I want to get a bit more into the routing algorithm in just a bit, but just to end this with the last paper that we've previously looked at, was I right in saying that this is much more of an let's say a general, almost like a review paper, or how would you describe it?
Yeah, I mean, I think we tried to make sure like we're contextualizing a lot of the work. So we tried to make sure the related work was like pretty inclusive because I mean, I think the field's really adjusted and improved a lot in the last 2 years. But I would sort of characterize this paper as fixing the two big flaws from our first one from Switch Transformers. The first was these models are unstable to train. So you'd be training and then all of a sudden the loss would just diverge, which thwarted a lot of our issues. Interestingly, it doesn't seem like the instability arises from a lot of experts. We were consistently able to train models, like our trillion parameter model, for instance, with thousands of experts, never really hitting any unstable sections. Really, it kind of came from like high flops or high computation expert models, even with like few experts. Those were highly unstable. And then the second thing that this paper sort of fixed was the sort of like poor fine tuning quality. So we would sort of pre-train a model, it would show like really significant speed ups over a dense counterpart. But then when it came time to fine tuning, say on like superglue or some like other task of interest, it would just be considerably worse. So I think this paper was just really trying to sort of like kind of patch up a couple of those issues we identified in our first work.
Yeah. I'm always a bit intimidated when a paper has a table of index by itself. Can you go?
This is something that Barret and I discussed. It's like, okay, should we break this up into multiple papers,
Yeah,
or should
yeah,
this be one? Because this is like a lot of work, and this is like something that we discussed. Like
yeah.
maybe in the future we should probably be producing like more bite-sized pieces of work.
When you talk about fine tuning, can you go a bit into more detail? Like what was exactly the problem? How did you also go about fixing it? So I'm not only interested in what's the final model like, but what does the process of debugging something like this and then getting to an architecture or a solution that actually works look like?
Yeah, I mean, it's sort of this like very interesting problem of like you want to there's really just like fundamental trade-off in whenever you're sort of doing this sort of like large scale work where you want to try to understand and characterize things at a smaller scale, understand scaling properties, understand like hyperparameter dependencies, but then you also want to be consistently checking yourself at the largest scales. And this sort of balance of like, okay, you have this much compute, you have this much time. Where do you allocate it? Do you do a lot of small experiments or do you do a few big experiments? It's kind of tricky. But I'd say part of our like findings were the first one was like, okay, well, characterization is we're not doing better on fine tuning. what's the cause? And it seemed like perhaps our cause is not that of optimization, it's that of generalization. So if you scroll down into section 4, you can just click on the link. We might be, yeah, exactly. Yeah, so this is an example that, kind of supports a lot of the trends we're seeing. On the left is a small superglue task. So this task has only 250 training sequences, so very small. And on the right is record. So this has over 100,000 training examples. We're showing sparse models versus dense models in the two plots. Blue represents the sparse train eval, and you can see it just very quickly gets to 100%, and it outpaces, in both cases, the small task and the large task, outpaces the dense model getting to 100% train evaluation accuracy. But when in the small task, we'll see the dense model in red actually outperforming the ultimate performance for the sparse model in orange, whereas for the bigger task, the sparse model does well. And so we kind of kept seeing this overfitting issues, and a lot of this was then led us to sort of investigate hyperparameters. And some of the hyperparameters can sort of be adjusted in a way to make the model less susceptible to overfitting. So you can use different dropout parameterizations, but also things like batch size and learning rate can inject more noise, which can also be sort of like a counter to some overfitting properties. So we tried, and then sort of consistent with this, a lot of these things were sort of more exhaustive studies at, say, a billion parameter scale. We then tried to continue to sort of fact check this against our larger model and make sure that these conclusions were holding. So I think it was just sort of the debugging process was, okay, what more precisely is going wrong? And then what are our levers that we can sort of pull in order to try to improve it? But a bit of art and science, really.
You observed, okay, we are probably overfitting because you saw the smaller the tasks got, sort of the worse these sparse models would ultimately perform on the validation set of those tasks. Did you? And you have.
It's not quite it's not always quite so easy as that, but it's sort of directionally. I think we have support of the hypothesis, but it's not every single small task does poorly and every large task does great.
Yeah.
But I'd say directionally, it seems to be a phenomenon we've observed.
You have also a bunch of experiments down here where you investigate some of these, for example, dropout probabilities. You also have expert dropout probability, which is one of the questions I had, in that you have a particular architecture, right, with these experts. And when I think about overfitting, in regular transformers, I have kind of handles. I can use adapter layers. I can only fine tune the head and so on. Did you ever investigate maybe only fine tuning some of the experts? Is that keeping others constant? Is that ever a thing? Would that work? Or can we make use somehow of the fact that we have these different experts and they're actually different functions?
Yeah, great question. And I think actually if you scroll down, we did a very naive kind of version of this, not where we freeze different experts, but we freeze all of the experts, or maybe only train all the experts and freeze all of the other parameters. I would say our findings were surprising in a bad way. So nothing really worked super well. So here you can see, and this is also, we only studied this on superglue, right? So it's far from exhaustive, but yeah. So one thing we tried was updating first all of the non-mixture of expert parameters only. And that actually performed about the same, which was kind of interesting. It's actually freezing the mixture of expert weights seemed to perform about as well as just updating the whole model. Then when we started to update only the mixture of expert weights and freeze all the other model parameters, the performance was actually really bad. And there was we still fully don't understand what's going on here. We have a few kind of half-baked hypotheses, but yeah. Then when we update only the attention parameters, things are worse. And we found a slight boost updating only the feed-forward network parameters that weren't the mixture of expert layers. But yeah, overall, nothing worked that well. But yeah, I think there might be some potential really interesting things of hey, maybe allowing only, a certain subset of experts to be fine-tuned. We did spend a little bit of time actually studying pruning off experts during fine-tuning. So like for a specific fine tuning task, if your pre-trained model has like 64 experts, can you just take like a subset of like 2, 4, 8, or 16 of them? Yeah, and we also didn't really get that good of signal with this as well.
Also, to some of your recommendations, they actually would be compatible with expert models too. So you're free to just like fine tune like the top
Sure. Yeah.
logit layer, or you could add in adapter layers. Yeah, we didn't do anything like really funky like you were suggesting, like, oh, we're only going to update experts like 3, 8, and 14 or something. Um, yeah, my intuition is that probably wouldn't work well, but I mean, I've been proven wrong many times. Um, yeah, we tried some like other things that didn't make it to this table or these plots. And yeah, again, we didn't really see like a significant boost. That said, if you are only updating like a fraction of the parameters, like, you get some memory savings. So, some nice things.
Cool. I guess there's almost an infinite number of things one could try with these things, like distilling experts, like distilling multiple experts into a single expert, so you have another expert that's again free to do some new task once you know that two experts are converging. Something like, I think
Yeah,
there's
yeah.
it's really interesting, right?
Or adding in new experts on the fly.
Yeah, a lot of possibilities, and that brings me a bit to this routing function that we talked about before and at the beginning, which seems to me is a really crucial part of the system. Yet, as you said before, very often I've just seen this being implemented quite simplistically. Maybe there's a linear transform and then a softmax or something like this. Maybe not even. Maybe there is some sort of a, you have some fixed keys for all of the experts, and then you route according to that. Do you, like, my intuition would be that this could be a powerful handle on what's, on my performance downstream, this routing function, especially also making this different during inference, any number of things. Doing a Monte Carlo tree search at inference time to be as accurate as possible, kind of like AlphaGo or something. Do you have an idea on what the power of the routing function in these sparse models is, and how does it work currently? Like, what's the latest and greatest, and how good is it?
Yeah, so this is a really good question, actually, and something we've actually spent a lot of time about. So I would say, actually, in this project, probably the thing I maybe spent the most time with is trying out different routing algorithms and routing parameterizations, but we ended up kind of going with the default thing, which I also think says something a little bit about the results of it. Yeah, so I would say my intuition is that the model actually works surprisingly well with a lot of different ways you can route the tokens. So like, we tried a lot of other routing algorithms. We tried making like the routing network larger. We tried like, some fancier ways of actually figuring out where you should send the token to. We tried, using additional information of like, oh, when you're routing this current representation, you have access to whether or not like it was routed, or like where it was routed before in previous layers, using like word embedding information too. But yeah, I think overall it seemed to be, kind of insensitive. We actually did find like one or two methods that improve things, but they could only be used in certain situations, so it was a bit trickier to just like replace everything. The current routing algorithm we're using is basically what the original one was doing, I think in Shazir et al. In 2017, when these kind of things were like really introduced into the LSTM language models. And I think, our newer work, and then also GLAM as well, we're using these kind of routing algorithms too.
Yeah, and also like one kind of like detail here. It's like, so right now we're sort of splitting out this little box and we're like, oh, this is the router. Um, it's not really an accurate characterization. It's like, yes, okay, you're mapping some vector into a vector that has like the same like length as number of experts. But if you just don't update that matrix, it still works fine, right? Because now just the weight matrices below you are just sort of adapting and just piping whatever activation they need, right? If you stop a gradient through that, then it's like catastrophically bad. But yeah, I mean, I've also sort of been surprised by the relative insensitivity to the routing algorithm. Like we've seen like, maybe some small boost here and there, but it hasn't been super significant. I think you'd probably have a better sort of like a bigger significance by actually just sort of fundamentally changing like the architecture. Like maybe there's like some wildly different approach for sort of sparse models that we're not considering. Maybe we're in some sort of like local min, and like these small tweaks on like, oh, okay, precisely how are we doing this? Maybe doesn't matter as much. And DeepMind's also explored some other kind of interesting routing algorithms. Like you sort of alluded to fixed routing algorithms where it's just like you're not even learning. They've also tried RL based routing algorithms. And I think it had like actually similar scaling properties. So again, kind of corroborating what Barret is saying, it's just like a lot of these things when we're kind of doing this like per token routing haven't really moved the needle substantially. That's been our look.
Yeah, and I think
Yep.
another important trend actually is that when we were experimenting with a lot of these different routing algorithms, we actually found that they did help models. And maybe when you had like a 1 billion parameter dense model-ish size. But then like as we scaled up the models, like actually a lot of the time, sometimes the differences would just like wash away as well. So it's kind of this interesting effect of when more scale is increased, like it maybe becomes a little bit less insensitive to some of these decisions.
Yeah, yeah, I can totally see that essentially that the rest of the network adjusts, especially if everything is trainable. What I would be excited about maybe is to somehow at inference time doing something smarter than, because at training time I can adjust to everything, right? But at inference time, maybe there's something that I could do, especially with regards to domain shift, domain adaptation, anything like this, where I could tweak routing in some way. But I guess that's also up for future work.
So there's a little bit of this, not tweaking the routing algorithm, but tweaking the capacity factor hyperparameter I mentioned a while ago. So this is basically the parameter that's going to dictate how many tokens are being dropped. And one cool thing you can do is you can have some capacity factor during training, but then at eval time, depending on if you want to use more or less compute, you can be either dropping more or less tokens and either kind of increase or decrease the performance, which is pretty cool. And the model's actually pretty robust to having that train and evaluation time. So that's actually kind of like a good lever for like, depending on if you want to use more or less compute during evaluation.
I think we have a pretty good overview now. I want to get a little bit into just the future prospects maybe also of this. We already talked about, with pathways, we could have heterogeneous things. Could this be pushed to some sort of limit? Whenever I see a distributed system, I immediately think distributed, maybe not even in a data center, but across users, across networks. Is there applications to maybe what is it called? Federated, some kind of federated computing, some kind of federated learning, where I could somehow contribute with my maybe confidential data, but I could still contribute to a whole compute process? Is there, I'm gonna say the B word, is there an application for blockchain distribution, something like this? Like, do you think about sort of the higher degrees of distribution here?
Do you want me to go, Barret?
Yeah, go for it. Me personally, I haven't spent a ton of time thinking about this, but I do think it's like very interesting. And yeah, there definitely seems to be a lot of really, open problems around this, especially given the growing amount of like fragmented compute, fragmented devices. Like there's so much compute around here. Like, how can you effectively utilize all of this, utilize different, data and stuff? I think it's like a super cool. And I think it was going to require a lot of really interesting research, because right now, the way we're currently training these models is it's all like synchronized lockstep typically, right? You're doing like, after each batch, you do these you send the gradients around and everything. But like, I think actually maybe the future of these models, when you're really, allowing them to be distributed across very different types of compute and everything, might actually now introduce like asynchronous training as kind of like the new paradigm. So I think that's like a really exciting space. But yeah, I haven't spent too much time thinking about it personally.
Yeah, and I think like as it would pertain to say like blockchain or something, like I think one problem with these expert models as designed in this way are these all-to-all communications. So over this sort of like, decentralized like peer-to-peer network where it's like, nodes are like, really far apart, inconsistent sort of bandwidth and stuff, that could be really tough if sort of your experts were sort of distributed among like many different nodes in this sort of like unreliable network where nodes are kind of coming and going. Like right now, all our systems are in this sort of like very constrained, fault intolerant area where it's like, oh, all highly internetwork chips that are highly reliable. And then so like blockchain would just have like a whole different set of like kind of problems that you'd have to sort of address, like unreliability and some of these other areas. Not to say, I think it would just like require some like additional kind of research, like just sort of adopting the model as is. I think would pretty poorly map on that kind of computing infrastructure. But I think there's something there that could be done.
Is there work on, because I see these works mostly here in NLP, yet Transformers kind of taking over the rest of the world. Is there work on how these sparse expert transformers behave in vision, in reinforcement learning, speech, whatever?
Yeah, great question. So absolutely, actually, there's been some really good work applying these models to like VIT based like image classification and stuff. And there, it's actually really nice because then you can leverage all of the niceties around like people figuring out how to get these working really well in transformers and kind of nicely map it over as well. There's also been some good work using these in speech as well. Liam, any other things to add on top of that?
I used to do reinforcement learning more full time, and some colleagues kind of reached out about doing like sparse expert models for RL. I'm not familiar with some work, but that might be sort of like another interesting avenue, but like for sure. So language, vision, speech. I don't know if there's been any video work yet. Yeah, but like high data, a lot of throughput, those would be like, really good areas. So I think video would be also really promising.
Yeah, I really like I feel like it feels very natural in these high dimensionality spaces that you really might want different parameters to be applied. Like when you have a video, like one, I think you don't want to be applying all the same amount of compute to every frame. But then on top of that, I could see like actually you really want to have different parameters applying to different, things going on in the video, because it's just going to be like wildly different stuff happening. So yeah, I think I'm very excited about these models for video as well.
Do you imagine that these models will just essentially right now they're competition to dense models? They're competing. You're tracking Pareto frontiers, how much compute, how well are they doing, tackling very much the same tasks. Do you think this will go on? Like, do you think these models might overtake dense models if we figure out how to handle them correctly? Or is it more like there's a killer app for each one of them?
Yeah.
I think do you want to
go ahead, Liam.
I honestly think that the future is going to be adaptive. Like, I don't think there's any way that like in 10 years, our models are treating all examples coming in with like the same parameters over and over again and the same amount of compute. It may not be this precise sort of like sparsity regime, or it may not be the precise sort of adaptive computation kind of like paradigms that have been put forth. But I view this sort of kind of work of like sparsity, adaptive computation as kind of like inevitable. Like, I don't think it's going to be considered like competition. It's just going to be sort of like integrated into a lot of like leading models. That's my expectation. I'd be really shocked in like 10 years we're training like a 100 trillion parameter dense model, and it's just kind of doing the same thing like over and over again for no matter what comes in. Just seems really strange to me.
What's the future for your particular research? Like, where do you see yourself going in the next, maybe not the next paper that you haven't published yet, but maybe a bit broader time scale? Like, what excites you and what are your next plans here?
Yeah, great question. I mean, I think the thing that really excites me is like what we were kind of talking about earlier of each input getting a different amount of compute applied. Like, I think right now the models are working well for each input getting different parameters. And I think, coupling this with like adaptive amounts of computation is like, I think really where I want to be spending time thinking about in the next, upcoming years.
Is there, I don't know, is you have something like Ponder, there's PonderNet and so on, there's these recursive architectures or recurrent architectures that sort of decide themselves when to exit. Would that be one thing, or do you simply imagine that each expert is kind of, one is the buff expert and one is the lean expert, and then the routing function essentially takes care of the different amount of compute?
Yeah, I don't know. This is a great question. I think, I don't know. I could see either approach potentially working, or maybe you actually want combinations, or maybe potentially something completely new. Yeah, it feels like the space is still, very exciting, and there's like a lot of really interesting different verticals being pushed. So the space still feels like, pretty young to me.
Okay, last question from my side. What's the connection of this to something like capsules? I don't know if you've ever thought about the connection there, but with capsules, I always think these abstract, very abstract things, very high level ideas flying around, and you here have something like very practical, very on the metal thing. Yeah, there seems to be quite some commonalities. Is that something that ever came up to you, or?
In the 2 years of doing sparsely research, this is literally the first time actually.
Okay,
I
nice.
actually should be going back to that work. I feel like capsules like yeah had a lot of like really interesting conceptions, but maybe like you're kind of alluding to, it didn't like map super well to the metal, so maybe that sort of like hindered its use. Whereas this is just like highly motivated from like an engineering perspective. We've had like some questions like, oh, what is like the neuroscientific kind of motivation of our work? And it's like it's really engineering kind of driven. So it's like, okay, what will be fast on our existing hardware? But yeah, I will revisit capsules and kind of see like, oh, okay, how could we actually map this a little bit better to the hardware? And like, I think that could be like, an interesting source of ideas.
Is there any last thing you want to get out to viewers that they should take away from this work? Any way that a regular person can get into this type of research? Anything like this?
Yeah, so great question. So actually, one thing we tried to show in our Switch Transformer work is that these models work pretty well, even if you only have two experts. So I don't want people to think that, you really need a supercomputer to run the models, or to, get benefits from having experts. Even having, I think, as little as two experts and running models could lead to developing really interesting research ideas, improving the performance and everything like that. So yeah, I definitely hope that, more people can continue to experiment and push forward these models.
Yeah, and then I would say like another interesting trend that I've been following is sort of in parallel to sparsity in these like really large models, is the idea of like, well, what if we just sort of like have the model sort of offload and like sort of do lookups, or look at documents and retrieval type methods. I think this is sort of like a very interesting area, and I'd love to see like kind of head to head comparisons of like, okay, do we want to try to encapsulate the knowledge into parameters, or do we want to just like keep it sort of like parametric, non-parametric type thing, and we keep the information kind of written in docs, or like what does the interplay look like? I think that's sort of like another really interesting avenue, like kind of comparing these things.
Awesome. Yeah, it sounds really cool. I'm excited to see what the future of these models bring. Yeah, Barret and William, thank you so much for being here. This was a lot of fun. I hope to see you again soon.
Yeah, this is
Cool. Thanks for having us.
Yeah, thanks so much for having us.